So if you miss out one, probably not going to matter too much. But if you're consistent and you can do well, pretty well for most of them, you should do well in your assignment score. Part of the intention is of course, to keep you on toes with the progress in the topics, and also serves as a quick review, and of course, give you marks, right? So this is one of the components where you can score easily. Can those behind hear me clearly? Okay, thanks, good, thanks. So now I have two hands to do whatever I like to do, good. So how to do well in this course? You ought to have read up the chapters, then come here and listen to class. Most likely it's not a repeat. It's not a repeat of what you have read, because here I highlight the more important parts and try to link you in with other topics by, for example, giving you examples, giving you worked exercises to show you some of the more salient parts of the topics. Okay. And you want to really do well this semester because next semester things may change, syllabus may change, right? So you want to clear on something that you really understand well rather than take up additional uncertainty. All right, time is close to 2:30. And we should be getting started soon. This week will be your first week having tutorial classes. For tutorial classes, my advice, let me say it up front, is that, of course, you try to get the right answer, but you don't try to copy answers from wherever sources you can get hold of, because you're not marked on your tutorial answers. And so getting it right, regardless of the method, is not the right way to do it. You should use that to challenge yourself to see if you can solve the problem. And if you have a different answer, try to debate with your tutor why your answer is right and his or hers is wrong. And through this discussion, this debate, you should pick up a lot. Okay? Tutorial sessions are for you to ask questions. If you don't ask questions and just hope for the tutor to robotically go through the answers, I think you are better off staying at home and watch video on the lecture, right? Because there's nothing much to be learned. Solution files will be given to you at the end of the Friday, around 5 p.m., 6 p.m. So don't have to really copy down the answers or take videos during the tutorial sessions. Instead, challenge the tutor on your understanding. Why is your answer, why is your solution, why is your method wrong or right, and things like that. Okay? Okay, time now is 2:30, and we should move on to today's topic, reason why you are here. You're here for a discussion of the random variables. So last session, we talked about the concept of random variables. And you can think about random variables as an algebraic letter, right, which is abstract, or you can think of it as having some kind of profile. This is not included. Or think of it as a histogram, because we understand the x and y axis pretty well, because the y-axis is the relative frequency, and we can always call that probability if we believe that the past tells us very well about the future. Okay, so that was my conceptual tool given to you last lesson. Today we want to explore more. What do you mean by a distribution? Where it can be classified very crudely but importantly into discrete and continuous distributions, right? So we have a bunch of lists here, and I divided it into 3 sections. We'll start off with the understanding of discrete probability distributions, what they are, how they are different when we draw them and look at them, and how they are the same and different at the same time with the continuous probability distributions. Mathematically, what must we do, especially for continuous, and what we shouldn't do. And finally, I have this little group of continuous distributions, and I put them kind of separately because I would prefer that today's lesson kind of includes all the distributions that you will expect in this semester. Yep, okay, so basically today is all about distributions. However, our in-depth discussion about student T, chi-square, and F, they will extend throughout the entire, all the weeks throughout the semesters. So today we won't talk too much about them, short of just saying that, introducing their names to you, that they exist in our scope of study, and they are continuous, and they have some formulas that are looking different, but they are essentially part of the family called continuous distributions, right? So, but our treatment of these named distributions will be a lot more. We have the formulas for them and so on, right? So these 3 distributions, student T, chi-square, and F, just for introduction's sake, let me put it more bluntly, for the purpose of the quiz that will include certainly lecture 2, you need to pay lesser attention on these than those on top. Okay, so but I like today's lesson to be a more modular, having a more modular content so that it includes all the distributions you need to know. So let's begin with understanding what is the difference between the two. Right, and these distributions are called known distributions. Those that we listed, such as uniform, such as binomial, Bernoulli, we have a name to call them. What I draw here is unnamed, right? There's no name to it. There's no standard way to draw them. I just drew them arbitrarily. And so this is what we call tabled distribution, where I can literally say this bar is certain at certain height, and the other bar is at certain height, up to my whims and fancies. There's no particular regularity to the heights and the relationship. So it's just a tabled distributions. So when we say the known distributions, we are referring to one of those listed just now, Bernoulli, binomial, Poisson, exponential, normal, including continuous known distributions. Okay. Basically, as we said, random variables can take up any distribution, and therefore it can take up arbitrary distributions with irregular shaped, right? Or it can take up pretty standardized pattern-looking kind of distributions, like what we see here. This looks pretty regular. There's a name to it. It's called triangular distribution, looking like a triangle. If we fatten the bar some more, we will see a triangular line. But that's not exactly what we are discussing, but it's kind of standard, very regular. This is also looking regular. This is following exponential distribution, but it's a discretized version. Don't worry, these are just examples, right? This is a continuous distribution, a continuous uniform distribution, and this is a bell-shaped looking continuous distribution that we all know. All right, so these are just examples. And what can we see from the difference in illustrations between discrete and continuous? That discrete distributions, there is a gap if we draw it. And even if you fulfill the gap, you draw these fat bars in between them, no gaps, right? But there is a gap between the labels, isn't it? That there is a 2.1. 2.1 is impossible in this particular discrete distribution. Agree? Yeah, because whatever data is given, we say that there is a 0.2 probability of 3 happening, yeah? But there's 0 probability of 2.1, 2.2, 2.9 happening. Yes, okay, so to that extent, there's a gap. Likewise here, this may seem continuous. The red line is continuous, but if you look carefully at the yellow tiny little bars, sorry, this is for illustration, so it's not meant for you to really examine it. But if you look at the tiny little yellow bars, the gaps indicate that there is a jump, right? Some numbers in between the gaps, they basically have zero probability. It's impossible for them to occur at all. And very unlike this here, if I have a 1 to 6 here, this continuous shading of the box from 1 to 6 illustrates that, yes, all numbers, 1.000001, no matter how many zeros you put in between the 1 and the last one, it exists. It is part of the distribution, right? So the way we indicate that is to draw, is to shade, is to color a continuous patch. Now, you can imagine why we would not start to count one ball by one ball by one ball like we did last lesson, right? Here we have many, many occurrences of events. We will probably use summation for the discrete. And because for continuous case, it is area, and area is best handled mathematically, not by summing dot by dot by dot, but rather we just integrate, okay? So this is just to give you some conceptual understanding, motivation, why we are talking about summation and integration. It's not trying to make it more complicated. There's no such need. We just like to count. But for discrete case, summation is easier to count, much faster, especially when the bars are quite related. Or every increment in x leads to a drop in 0.05. So it's quite regular. And then we can sum pretty easily. Same thing for summation, for integration. If there's a regular function describing the height, we can find the area rather easily. Now, you may have forgotten your calculus, and that's okay, but you need to know this. That's when I need to find the area, I need to integrate. This is not too much to ask of you, right? But how to integrate certain technical and very complicated functions, yeah, that needs a bit of additional help. But I need you to understand why we need to sum, why we need to integrate, okay? Next, let's look at properties of discrete. Let's zoom in on the discrete part, okay? The discrete probability. First, what do you mean by a discrete distribution? 2 points. These came out in exams before. They may ask you to verify that this is a discrete distribution. What is a distribution? Well, number one, that all the bars, what this says is all the bars are above sea level. Okay, for discrete distribution, the P of x equals to x. This is x. Okay, this is the probability. And what this means is that the height is the probability. Now, I may say this sounding more like a casual reminder, but very soon we'll contrast with continuous distribution, and it's a world apart. Okay, so the height is giving us directly the probability. Now, of course, in business, we would like to know the probability. We want to know probability because we decide, is this likely to give me investment returns or not? Is this likely to give me my break even earlier or not? Right, and so on and so forth. Huh? So we like to know probability. And this x-axis, the range of possible numbers that can happen, this is called our sample space. So on the diagram, on the graph, we may call it the x-axis. But remember last week, what is sample space? Sample space is a set of all numbers that the random variable can pick up. Here, what are the possible values? If we just limit to this diagram, this is the full definition of the discrete distribution, then x can validly take up only values 1, 2, and 3, right? Because the fact is that there's no indication that it can take up 0, 4, 5, 6, and so on. So the sample space, here's how we say it, the sample space of x is 1, 2, and 3. Yeah, okay? And the height of it is going to be given by the y-axis, for example, 0.5, 0.3, 0.2. So first thing first, the first property to verify that it is a distribution is all the bars, all the probabilities are above 0, the sea level. That's easy to see and almost trivial, but if this is an exam question, you have to say these 2 points. As we can see, all the probabilities are greater than 0, hence it satisfies the first requirement. Clear? Right? You have to say this. You can't just assume that we can check for you. We, the grader, can check for you because you're the one being examined. Point number 2, when you add up, here is the summation. I need you to understand this. This just means when you add up what? Add up the body of the summation. When you add up all the probabilities, but what about x? Which value is x? X ranges over all the values in the sample space. Yeah? If you add up the probability means the y values, right? But when x equals to 1, x equals to 2, x equals to 3, all the probabilities, when you add them up, 0.3 plus 0.5 plus 0.2, is it equal to 1? Of course, I quietly make sure they all add up to 1. So, is it equal to 1? If so, if it adds up to 1, exactly 1, not more, not less, and it satisfies 0.1, that all the bars are above sea level, then we can validly call it the distribution of x. Otherwise, you can at the most call it a histogram, and it's not necessarily a distribution. Okay, so to be a valid distribution, says the exam question, then you have to respond by checking these 2 points. Clear? Quite straightforward to check. How to describe or execute this verification will require a little bit of skill sometimes. Diagram-wise, it's easy to see, but let's look at this example. You're given this discrete distribution. Where do we know it is discrete before we draw the diagram? Where do we know it is discrete? Well, x can take up all the values from 1 to, can it take up 1.5? Well, not as far as I can see, not from this definition, right? So, therefore, it is a discrete distribution. But wait, are we sure it is distribution? Show that it is a distribution. Now, clearly, it is a discrete kind of diagram, but is it a distribution? So, we check. Are all the probabilities greater or equal to 0? Well, 1/6 is always greater or equal to 0, right? So the first point is stated here. Yes, all the probabilities are greater than 0, greater or equal to 0. Secondly, if we add up all the 1/6, now how many 1/6 are there? Well, we have 6 pieces of 1/6, so when we add them up, right, so as to say, we can say summation of x ranging from 1 to 6 of all the 1/6 is equal to, well, that just means 1/6 plus 1/6 6 times. All right, and clearly that adds up to 1. And we are done. We have shown that this is a distribution. Clear? As simple as that. Now, of course, more complicated ones, we can, we also go by the same rule, but how to sum, that we might require certain special techniques. Now, before you start flipping through all the summation tricks and all that stuff, not to worry about that. I won't challenge you with all the complicated summation techniques that is ever known to human beings. Okay, so what I do want you to know is that yes, summation is very much part and parcel of evaluating distribution and probability. And if I give you something simple as this, I'm testing you on the concept, not your mathematical prowess. Agree? This is so easy to check. But do you know you have to check this? That is the probability statistics part of your knowledge. That you have to know. All right? Okay. Next is the idea of cumulative probability. Cumulative means like your CGPA, right? Cumulative. You keep on adding up. What does it mean mathematically? It means you keep on piling up the probabilities from the left. From the left. I put a little note here, but you might write to yourself, right? Start from the left, the extreme left. If the extreme left starts from minus infinity, then you start from minus infinity, like the normal bell curve, right? So this is a fixed definition. It always starts from the left because the less than equal to sign will never change. It's part and parcel of the cumulative probability definition. So let's take a look. P of x equals to little x is 1/6. Again, same distribution. We have confirmed that this is a distribution. Find A. Find C of x equals to 2. Okay, I don't know how to find C of x equals to 2, but I go by definition. C of x equals to 2. Sometimes written as C of 2. This C, of course, here can be confused with the counts that we started off with, right? So sometimes we write CDF of 2, the cumulative distribution function, but they are just one and the same, cumulative probability. So we would then say, find this. What is this? This is essentially finding all the probabilities that are less than or equal to 2. Agree? Because I just copy and pasted, but changed the little x to 2. Okay, so in that case, what I need to do is, because this is discrete, I can list it out one by one because it's easy enough. And because each piece translates to 1/6, and so the final answer is 2/6 is 1/3. So that's easy, yeah? And we got it here, yes. And what if, and that's not usually what we do, what we want to do is we obtain a formula, right, such as this. C of x equals to little x in general, so that I can at will pass in x equals to 3, then what is the cumulative probability up till 3? All right, and pass in x equals to 4, what happens then? You know, I don't have to keep on going through from scratch all over again. So what happens then is to sum up everything from, I change the dummy variable from x to u equals to 1, 2, 3 until x. And each time, the probability is constant at 1/6. In that case, if I have 1/6, then the answer is 1/6. If I have 2/1/6, then the answer is 2 times 1/6. So in general, if I have x 1/6, then it's x times 1/6. So that will be my formula. Yeah? So having a formula is nice because I can anytime plug in an arbitrary value of x and obtain straight away the cumulative probability. Okay, so far, I mean, this is something new, so take a bit of time to digest this. But remember, here, something trivial but very important. This is less than or equal to. It tells us to start from the extreme left, whatever extreme left means for the distribution. Number 2, the equal sign is inside. So there's never a hesitation. C of x equals 2. Does it include 2? Sometimes it does, sometimes it doesn't. No such thing. It always includes 2. Okay, the equal sign is inside the cumulative probability. 2 other concepts that are related, the mean and the variance. Where is the average level and how spread out they are, okay? Just by way of feel, in a 2-dimensional problem, why I use 2-dimensional? Well, it's trying to make it easier. Because our eyes can access 2-dimensional images rather quickly as a statistical processor, right? So let me ask you, let's say these are galaxies and stars, okay? But they can jolly well be some kind of ink spread and so on, okay? Now, if this is the ground, which cloud has a higher average? Is it A, B, or C? You will say it's C, right? I have not even given you any number, and you haven't done any summation, integration, whatever have you, but your eyes can tell. C has got the highest average, yes? Which has got the highest spread? And I haven't said what is spread, but you say C, right? Because C is more like this, right? All over the place, more thin out, right? But which one has the lowest spread? B, yes? Which has the lowest mean? The lowest average value, the lowest position. You might say B, but if I dot here a bit more, someone might argue, but wait, C also touches here, C is lower, you know. But you won't say that, right? Because I'm saying that on average out basis, roughly where's the center of gravity. Can you see that? So our eyes can tell very immediately, B, we all say B has got the lowest mean position, height. C has got the highest height, tallest height, biggest height. The spread, C has the biggest spread, B has the lowest spread. Okay, so that is it, the qualitative feel to it. Where's the mean to it? Because when you gather data, you will have this kind of phenomenon. And you have only very little attention space from your boss, your superior, your customer, your commercial, your management. They will have only a 10-second window to hear. How was your work? How was your survey? How was the product going? how was your fund going, and so on. Fund, F-U-N-D, you're managing the fund. You only have a few seconds to summarize your situation. What would you say? Now you can say the average performance is this, not bad, average has increased. Something like that, right? So that's how to summarize a lot of data into a one-piece information situation. We do that all the time. We do that all the time, right? Maybe that's not conscious, but now let me bring it to your conscious forefront. That when we say expected value, that's a more formal term. We calculate by tagging in a little x times the probability, then we add up everything, and that's all. Just now when we did the verification of the distribution, right? Remember this part where we say check whether it is a distribution. Check whether this is a distribution. We added up everything inside the sample space, but only the heights, the probabilities. Now what I'm asking you to do is to just multiply by x before you add, that's all. Okay, and if you do that, the entire resulting value is called the expected value, or else the average. Why is it an average? We talk about it as adding up all the x's times the relative weights given to each. And since the relative weights add up to 1, remember it's distribution, right? So it is already an averaging process. Okay, so a quick example here. So we take the same distribution here. It's the same distribution. We have verified that it is distribution. Calculate the expected value. We check the expected value first. The formula, strictly by definition, says add up all the probabilities. Well, they are all 1/6. Just now we added up all the 1/6 times and we got 1, right? But this time, you got to multiply x into each of the probability before you add. So we get 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3, and we factor out the 1/6 to get this. So essentially, we add up 1 plus 2 plus 3 and so on. That's the mathematics simplification part. But the idea is we stick in an x first, then we times, then we add. And you find that this is a very correct way because it gels with our weighted sum of the averages. Basically, we're implementing that via the probabilities, where the probabilities are the weights. So if you do your summation correctly, you should get a 3.5. Okay. Now, this is also the part where perhaps we can look at this. Now, your calculator is immensely powerful, in case you didn't know. Right? So underneath this math button here, right, is a list of functions. I'm not going to go through everything, but just very quickly, there's this thing called summation. Okay, and this is what you want, right? So when we sum, it tells us have a variable, and this xt theta n button is your variable. Whether we put it as x here or y here or z here, you will only have one choice. It's called x. And we want to go from 1 to 6. Every time when the calculator adds, you want the calculator to add x, which is the same x, times 1/6. Right? So this is what we have as the expected value, isn't it? Yeah, so if you do that, then the calculator will give you 3.5. Now, this is no big deal because the 1/6 is so simple. But if I give you a complicated probability function, 1/x squared, then life starts to get very interesting. You start to perspire a lot. But if you enter the 1/6 as 1/x squared and just let the calculator do its work, all right, then you would be able to find the expected value. So I would really need you to learn the expected value concept, but if summation is going to come in the way to, give you some resistance, then here's one way to help you. Yeah? So your calculator can do that. Next, variance. Variance has a similar but slightly different internal than expected value. So if we are clear with expected value, all we need to do is, instead of multiplying by little x, we multiply by the square of x minus the expected value of x. So you need to have the expected value of x first. Essentially, the variance tells us if this is the expected value of x, okay, x will be an arbitrary value here. Let's say this is 10, this is 8. So x minus e of x x minus e of x will be this difference here. So this is x, this is e of x. So this is x minus e of x. Agree? Okay, and we like to know the square, so we give it a square area. Basically, it's to add up the square. And if you think about it, this square here gives us a square area, and it is the weighted sum average of all the squared areas induced by the data points with respect to the e of x line, the average mean line. That's all to it. And of course, if the data is far away from e of x, you have a huge square, right? What happens to your variance? Is it going to be large? Yeah, you can say I have a tiny weight to it, but it will be enlarged anyways, right? So large spread results in large variance, small spread results in small variance, which is nice because now we have an automated formula way to calculate what our eyes can intuitively tell us. Now, if you don't find that amazing or surprising or impressive, think of how you can teach a robot to recognize, tell me, is this bigger spread than this? And you will have a hard time if you don't understand the concept of variance. Because variance is the one that converts all the data into a single number that says C has got a variance of 100, A has got a variance of 80. Then you compare, then you announce C has got a larger spread. What has any use with that? If C represents the joint probability of two stocks, maybe US dollars and stock, Dow Jones with another stock and so on, then you will find that this is riskier than A. This portfolio C is riskier than portfolio A, don't you think? That your resulting returns might be anywhere here, but A is pretty well defined. B is even better if you can, but it's got a low return, low average return, right? So this kind of analysis, it's up to your imagination as to where you apply. But the fundamental definition of everything sits on this formula here, the ability to convert this kind of pattern into a number, and that's very useful just by its definition alone. Okay, so let's come down to the bread and butter. How do we calculate it, right? So still using the same distribution, calculate the variance. This kind of question a few times came out in the exam last time. We have the variance being the summation of 1 to 6. We are now using the second version of it. How come? Because if we calculate the e of x, then this becomes, okay, let me exclude this. The summation is one calculation on its own, and the e of x is another calculation on its own. So here, the first calculation, the first red box, doesn't have e of x. So we can just focus on x squared times the weighted sum, which is the probability, and then use the summation to calculate it, right? So in case you wonder, what's this value? Now you can figure out, right? What's the value? Yeah, so if in exam, you need to calculate variance, for variance, you need to calculate e of x anyways, right? So you calculate the e of x, and then you go back in, press enter to copy and paste, and what you do is you do an insert here to calculate the square of this, and you save a lot of time retyping. So this value minus the square, this is not yet the variance, this is only the first red box, minus the square of 3.5, that will give you the final variance. Of course, if you take the square root of variance, you will get the standard deviation. Right? So this is as straightforward as it sounds. Okay, so here's a list of all the standard, or rather the known distributions that you are expected to be familiar and be very expert with. And of course, you can learn the formulas. I won't try to derive them or prove them. It's not a mathematics class. But more importantly, what's the feel to it? When can we use some of these distributions? We use distributions to try to mimic real life. So there's this real life business problem, and we like to say, should we use bell curve? I heard bell curve is applicable everywhere, but not all the time. Suppose your business problem is about do or don't. Should I invest in this stock or don't? Should I study in NTU or not? It's a binary decision. So what do? Some of you don't need to tell me who you are, might have tossed a coin, right? Yeah. If you toss a coin, then you would use Bernoulli distribution to mimic the outcome of throwing the coin. How come? Well, because if it's not a fair coin, for example, if it has a 70% chance of showing head, where we say head is represented by 1, then it is a biased coin. Then you throw. What it means is that 7 times out of 10, we expect the coin to show us what? To show us 1, where 1 is success. 1 is coming to NTU. 1 is investing in the stock. So whenever you have binary 2-stage events in your x-axis, can you shout to me what's the x-axis again? The technical term for it is the S and the S. Just a moment ago. What is this? It's not the x-axis. X-axis is a diagram. But the 0 and 1 here are the possible unique outcomes that your event, your coin will show. What do we call the set of all possible unique outcomes? The sample space, right? The sample space. When you say things like that, say during an internship interview, you sound very, very impressive. Yeah, it is. When you use the right technical term, you impress the hell out of the interviewer. Is it? I never learned that in my class last time, in the university, somewhere along Clementi, they didn't teach the right thing, I think, So you have to use terms proactively, voluntarily, to say that very, very technically accurate sounding thing that you intend to say. Then it is impressive and you are speaking like a pro, okay? So when we talk about throwing 1 coin, we say Bernoulli distribution. If we talk about 10 coins, then we have 10 Bernoulli distribution, but we're not handling 10 events. We're talking about 1 event of throwing 10 coins, right? So it feels like 10 events, but I'm adding them up because when I throw a coin, it has 0 or 1. It is tail or head. If it's head, let's say it is 1. And I throw 10 coins, it feels like 10 separate events. But no, my intention is I want to add up all the heads. I ask myself, if I throw 10 coins, what's the probability that I will see 5 hits, or 3 hits, or 10 hits, for example? If you ask that question, that is the total sum of successes in a fixed number of trials. So I throw 10 coins, and I ask how many hits, right? Then I'm having a binomial distribution as the prime candidate to mimic that business situation. Okay, I have 3 projects for investment, or else 5 stocks that I want to invest in. I put in the money, and so on. Then I ask myself, what is the probability that I will get returns above my investment? Some will lose money, some will earn money, right? Having 3 stocks or more giving me returns beyond my principles. That kind of question, first of all, is it fixed? 5, right? And I'm asking, do you have returns or not? I'm not asking how much is the return. I'm not asking, am I going to exceed 2 times my investment principle? I'm not asking the quantity. I'm just asking yes or no. Correct? Binary, right? So each stock on its own, is it a binary event? Then yes, then it's like throwing a coin, right? Assuming all the stocks have equal chance, because when I throw the coins, all the coins must be the same. Huh? Okay, so assuming each stock has equal chance of returning me profits rather than making losses for me, then I'm asking a question that has finite number of coins, each coin having the same probability of incurring profits or loss, right? And I'm counting the number of stocks that give me profits. That is a prime candidate for binomial distribution, right? So it fits all the criteria. Is this a prime candidate for normal distribution to model my question? Well, not quite right, because normal is continuous, and I have 5. 5 cannot be approximated by minus infinity to infinity, right? No matter how you squeeze the bell curve. So it feels strange. So if you force a wrong distribution into your business situation, you're going to get, you can get a number out of it, out of your calculation, out of Excel, but the number is going to be very distorted, and you don't want to trust it. What you can trust on is, let me apply binomial, because this fits the most. If I use Bernoulli, that's one stock, but I have 5 stocks, right? Something like that. So when you go by this reasoning, your reasoning will be appreciated, because when you write your report, the probability is going to be 0.72. And people ask, how come you arrive at that probability? You say, because the situation mimics or rather justifies the use of binomial distribution. You see it's finite trials, and assuming, there's one assumption, we assume all the stocks have the same probability of returning profits, right? So people can challenge you on the profits on this assumption, but nothing is perfect, right? Because if they go beyond binomial, they look at Poisson, not quite right. Not quite right. We'll see why in a while. It also has got vertical bars and all that, but not quite right. How come? Okay. They look at uniform. Uniform has got 1 to 6, but all these are, well, you're saying that uniform distribution, one event has got 6 outcomes. But I'm saying that each event, each stock has got only 2 outcomes, profit or loss. But uniform distribution, one event has got 6 unique outcomes, correct? That's not my cup of tea here. Yeah? So if you look through, binomial is the best. Now, because we are talking about binomial, let's look at Poisson. How come Poisson doesn't fit my question here? 5 stocks, whether 3 or more will return me profit. How come Poisson doesn't mimic well? Binomial has a requirement and fits very well when you have finite trials. For example, 5 stocks, 1, 2, 3, finite. That doesn't go to infinity. Whereas Poisson, what happens? Always go to infinity, okay? There's no control over the sample space again. Right? So sample space plays a big role. Our business problem has got, my business question has got a finite sample space, 1, 2, 3, 4, 5. What's the answer? The answer is 0, 1, 2, 3, 4, 5. No stock giving me profits, 1 stock giving me profit, right? So the answer is finite. But Poisson, you can't control the sample space. It always goes from 0 to infinity. The only thing is that the probability gets smaller and smaller and smaller and smaller. It diminishes so fast that the average is still finite. It's not infinite. Okay, so we see the average values, the E of x. Now that we understand what is E of x, the average value for binomial is n, the number of coins, times the probability of each coin giving positive hit. The average value for Poisson is just lambda. What is lambda? Lambda is the rates of arrival, customer arrival, the rate of arrival. Okay, so for Poisson, oh no, it deserves its own space. Huh? Poisson is important. So for Poisson distribution, the important number is lambda. It is the rate, or rather the average rates of arrival of events. Now that sounds a bit vague, but let me try to draw this animation. I have a cafe, okay, and I have people, customers, coming to my cafe. And if I use a camera to monitor people coming into the door, the front door, and I use, I don't know, Apple's iMovie or whatever to unreel this CCTV footage, then you can see that this is time, right? So this is first customer, second customer, third customer, fourth, fifth, and so on, okay? So, okay, why do I draw this? Now, the thing is, how do I see or visualize lambda? The way we go is this. If I mark the axis as time and I partition them into 10-minute interval, okay, so each one is fixed 10 minutes. You follow what I'm trying to say? Okay. Then I count the number of people within each 10-minute interval, because the people are the events I'm watching. Is my cafe making money? And one very important yardstick to measure is the number of customers arrival, right? If no customers, don't even talk about money. Yeah. So I like to know a lot of customers or not a lot, and how do they arrive? So if I use Poisson distribution, what it means is this, that every 10-minute interval, all right, I will count the number of customers. And how many do I count here? 2, right? 1, 3 here, 1 here, and it's always integer. It's always integer. There's no fractional. It's either you lump into the first slot or the second slot, something like that. So there's no fractional customer count. And we do this. And once I do this, what I do is I will then build a histogram of this. How many times, if I call this, because this is a sequence of numbers, a sequence of numbers is a random number, a random variable. So a random variable can be thought of as a histogram in the sense that I can ask how many times, that is, how many 10-minute windows did I see one customer? Here, 1, 2, so I will get a 2 here. How many times do I see 2 customers? I see a 1 here, something like that. Okay, you get the idea how I build a distribution out of a time series number. Don't confuse the two. What I have written here is a time series number. It is based on first time interval, second time interval, third time interval. This is a distribution. There is no time element there because I count across time. So I eliminated the time axis. So how many times did I see a 3 count of people in the 10-minute window? 1 count of 3. That is why the vertical axis is 1. Okay, when you do this, what Poisson distribution says is that if the customers are all independently minded, they don't collude, they don't call each other and say, hey, you want to go to Chinchika's cafe or not? Right? If they don't do that as a colluded group, then each of them spontaneously, oh, I'm thirsty, they will walk towards my cafe. If they do that, then the resulting distribution ought to follow Poisson distribution. So we say X follows Poisson distribution with a parameter lambda. That is to say, if the average rate of arrival is 2.1 customers per 10-minute window, then my lambda will be 2.1. And the average can be fractional, it's okay, no problem. Follow? All right. So if you don't believe this, some business operations, some of you taking biz ops, right? And some of you already taken. So some of you in business operations, you have to do a project, and some of the project groups study queuing systems and all that, and they literally go and measure the time and the arrival and all that, and they build a histogram, and it's amazingly, some of them don't look like Poisson because other factors are, because you guys go in groups or something like that. But some of the resulting histograms look very much like Poisson because for that particular restaurant or that queue, people come individually, something like that. And it sort of really exhibits this quality. Okay, so Poisson is very useful when we talk about customer arrivals. That's why I put it here. All right, and it doesn't have to be customer. In physics, a lot of times you will also encounter Poisson studying the gamma particles from Andromeda galaxy, what we call the rare events, right? The rare events. Those kinds of situations, also Poisson. So very, very important. Whatever you learn here, they're all very important. And one more discussion to talk about before we go for a short break is the table distribution. This is a place where all the heights, remember that the heights, they are the probabilities, right? Okay, the heights gives us the probability, and because they were regular just now, for example, the heights of uniform clearly is regular because it's given by 1 over b minus a plus 1. That's a fixed constant, 1 over 6, 1 over 6, 1 over 6. The height of binomial is looking horrendous because of the combinatorial possibilities, but it can be done. It can be accounted for by a formula. Poisson distribution is looking Poisson, right? It involves exponential and so on, but we can still calculate it using calculator, no issue. Yeah. Table distribution is different. It is when arbitrariness comes in, right? We don't have a way to really say why the second bar has to rise and the third bar has to fall by that amount. Then we just populate it with a number like this, okay? So when we do it this way, then this is a table distribution, and you will get this a lot in your exam or maybe even the quiz because this is what we frequently see in reports. Your frequency here, I give you how many? 15, 5, 20 counts only. But in real life survey, this can be 2,000. And we wouldn't give you the raw data for 2,000 counts, right? So we will, most of the time, summarize them. And you will then be asked to calculate mean and variance. Okay, here is sort of a quick trick here. Now, you certainly need to know the reason why we calculate it this way, because this is by definition. To calculate the expected value, you use x times the probability, right? But last week, I think I also briefly showed you that if you enter the value as 1.1, 1.7, 3.2, and 5.8, yeah, and you enter into another list, doesn't have to be the neighboring one, but let's do it there. The probabilities, so the 0.25, the 0.45. Last week I kind of did it once, but it was frequency. But your calculator is able to accept fractional frequency, what we say as probability here. Calculator treat it as fractional frequency. So we're going to do a one variable because we literally have only one random variable here. Yeah, because this is the x, this is the y, right? So one random variable here. So we're going to do a one variable analysis where the x values, the sample space is given in L1, and the frequency, this is where you tell the calculator where your probabilities are, right? So it's in L2. So when you do that, you find that it will calculate for you the tabled distributions, mean, and the standard deviation, right? Where is it? So this is the mean and the standard deviation, which is, sorry, that's the variance. If you take the square root, so I need to take the square of sigma x. Just a quick trick, you press vars, variable, then go to 5 for statistics variable, and you look for sigma x here. So it's function 4. All right, so I just need to square this, and I should be able to get the variance that we calculated based on theory. All right. And the idea here is that when we do a one stat analysis, one variable stat analysis, right? Let's look at it again. There's one part that I want to point out here. The sample standard deviation is missing. How come? Normally we get 2, right? Yeah. How come when we enter this particular table distribution, in fact, all tabled distributions, when you enter and calculate it this way, you will see that the Sx is undefined. In other words, there's no means of saying a sample standard deviation is how much. The reason is, and here is something you should take note of, because in exam questions, this is an implied knowledge. When you are given a distribution, are you given a sampled distribution or a population? Do you treat a distribution as a sample or as a population? That's the main question. Because if you treat a table as a sample, then Sx ought to be defined. It should be there. And the fact that it's not there is telling us this should be treated as a population. That's right. Whenever the word distribution is mentioned, it is implied that we have known the universe, or at least as far as the subject that we are trying to study. We have known everything, and we are telling you, right, or you are telling the reader, that my population behaves in this way, you know. If you measure, they only occur as 1.7, 3.2, and 5.8. And I tell you that 3.2 occurs the most frequently. And I've accounted for everything because all the probabilities add up to 1. All right, so when you have that distribution, remember what is distribution? The probabilities add up to 1. When you have that in that kind of behavior in your frequency, because the verticals add up to 1, then you find that the Sx is absent. And basically, you should already know that when someone says, I give you a distribution, they are talking about knowledge of the whole population. They know everything about the population. There's never a case or a situation where I give you a set of samples and I call that distribution. There's never such a thing. Clear? All right, so just make sure the terminologies are clear. All right, let's take a 5-minute break. When we are back, we move on to continuous distribution. We'll resume at 3:20, 3:25. Okay, are you back? All right, let's resume our discussion. And we like to focus more on the special treatment that we have to pay attention to when we operate on continuous probability distributions. Okay? There are a lot of overlapping areas just because the sample space, remember what sample space? The set of all unique outcomes that our experiment can expect. Yeah? What is the sample space of your height? Well, it's probably what, 0 meters? Impossible, right? 0 meters until 5 meters, maybe, yeah? So that will be the set of all possible height of any of you, right? The possible outcomes. So first thing first, when do we get continuous probability? We get continuous probability by assumption. That is to say, we assume that certain measurements ought to be continuous, and we use continuous treatment. Mathematically, we use integration, we use functions instead of tabulating the probability and the numbers. What are some of these assumptions, assumed measurements, such as distance, time, weight, temperature, a lot to do with physics, right? But also money. Money, we have the smallest denomination, 1 cent, but we assume there is continuous increase in value between 1 cent and 2 cents. Yeah, that's the assumption. Energy and things like area, which is length, distance times distance, volume, which is area times distance, speed, which is distance divided by time, all the derivatives, the ratio, the products, and all that. They will be assumed or modeled. And I say modeled because studying whether actually in real life they are discrete or continuous is the job of physicists. That's not our job. But we model them because we want to achieve certain desired outcomes, like making a decision, invest or not invest, is the money going up or down, going up how fast, and so on, right? So we mimic these quantities, these measurements, as continuous random variables. Now, do we say that when we throw a dice, let's use a continuous distribution to model the outcome of a dice? Not really, right? Because the dice has 6 fixed faces, right? And we already have finite outcome. It's easy to handle. We should use discrete probabilities. But profit of a company, who is to say that it doesn't have a one-time, suddenly a big earnings, right? Who is to say that it doesn't have a sudden cash injection? Who is to say that it doesn't have a sudden product launch like Apple, right? So money basically is continuously going from one to another point, and we ought to use continuous distribution, whether it's bell curve or whatever curve. Okay, so that's giving rise to continuous probability. Now, a little bit of a sidetrack is that things like time we use continuous. So if there's an exam question using time as the main discussion topic of measurements, you ought to be suggesting using continuous random variable. But some of you are very good with things and you say, no, I look at the clock, it's digital, it's always minute by minute, second by second. I look at my analog watch and the finest delta I can read is not infinitely precise, it's also 0.1 second, right? So it ought to be discrete. Now we will not argue with those, okay? In real life, almost everything that we try to measure will be discretized because your weight, even if you go by the analog weighing, you still approximate to the nearest scale. You measure using your ruler, you still approximate to the nearest isn't it? So you discretize it in real life. We're not going to argue about, those should be discrete and why are you saying we're not talking about those. We're just saying that we allow for the continuous change in our underlying model. So the word model is important here before you get too confused as to in real life it should be discrete and that kind of thing. Huh? All right, let's get past that. Bread and butter, right? What's the difference in the treatment of continuous distribution? First thing first, let's look at one right into our eyes. This is a continuous distribution function. It's got a height and an x-axis. The x-axis remains as the sample space, thank goodness. So there's something that is still there, but the height suddenly has changed. The characteristic has changed. It's no longer interpreted as the probability. Notice we say something new here. It's the probability density function. Before you try to read between the words and say what is density and all that, let me just save you from that infinite loop. And that's to say that this probability density is just a word, all right? It's just trying to say it is not probability. It's just trying to say this is the height of the graph. You can just think of it that way, all right? PDF, the probability density function, and this makes sense only for continuous distribution. PDF of the continuous distribution is referring to the height of the graph at a particular point. So at a particular point x, when x is 1, for example, we get the height 1 over 1 square, and so it is 1. Can you see that? The height is literally 1. But obviously the height is not the probability, right? Because the 1 bar here already is 1. And we are unable to add up everything as 1. So where is the probability? Well, the probability now is like butter jam being spread out throughout. The probability is found as the area underneath the PDF curve. First thing first, the PDF curve starts abruptly at 1 and then crawls slowly to infinity. The area is the yellow area, or rather, sorry, the probability is the yellow area beneath the red curve, beneath the PDF curve. If PDF is undefined between 0 to 1, then there is no area to speak about in that region. Clear? As simple as that. Right? So it's like you cast a light on top. What's the shadow below? That is your probability. Now, obviously, between 1 to 2, there's a lot of probability, right? We can already tell visually. From 4 to infinity, even up to infinity, we say that's unlikely to happen. How come? Because we know that probability equals area. Please write that down. For continuous distribution, the probability equals to area and not the height. This is the main difference between area under PDF. Whereas for discrete probability, this discrete distribution, the height, the y-axis directly gives you the probability. So that's one difference here. Clear so far? All right, so when we look at the diagram, and in exam, we can give you a diagram, we can give you a function like this. The PDF is this. Calculate the probability between 1 to 2. So what do? If it's probability between 1 to 2 like this example here, right? Then what you need to do is you need to integrate. Yes. So we try to integrate from 1 to 2, and we change the x to u just to give it a different name. The integration of 1 over u square is negative 1 over u. This one you will take out. They require integrals, a separate file that I put on NTU Learn. You can find this basically doing a pattern match. Oh, 1 over u integrate is, then you look at the result, then you copy minus 1 over u inside. Okay, so what you do then is minus 1 over u. When u is 2, you plug it in. Wait, let me finish first. Okay, this is the theoretical part. You plug it in, you get minus 1 over 2. And this minus is required, okay? This is required. All the time when you evaluate, this is required. So minus 1 over 2 minus another copy of the minus 1 over u, but this time u takes up the value 1. And you have negative 1 over 1 here. You see that I just copy and paste. I don't try to calculate on the fly. When I do this, then it's negative half minus minus 1, which means negative half plus 1. And end up we have half here. Follow? Okay, now let me show you the easier way. That's where your calculator comes in again. So notice the math button, right? The math button. If this button is spoiled, you probably want to buy a new one. Okay, so math button here, you go to the bottom, and there's this very innocently looking name called function integration. FNint. Okay, so when you press that, it gives you the integration sign, lifesaver. So it says integrate from where to where? You say 1 to 2. Okay, and the inside is the PDF. Inside is the PDF. You see that the 1 over u square came from the fact that we were told that PDF is 1 over x squared. So we enter 1 over, and you better bracket the x squared. Now we need the x squared, the dummy variable. Again, same thing here, the x. Okay, x squared, and you close it. So this is 1 over x squared. Oh, sorry, I entered 1, 1. So the top number should be 2. And the last value that you need to enter is this box, which is d of what? Run which variable, which is x again. So you just do that. Okay, which is literally what I have on the screen here. My slide here is just changing the x into u. Can you see this? I'm entering this thing here, which is just following what the summation says. And it gives us 0.5, so you just say it's 0.5. Okay. So what's the probability? What's the probability of x between 2 to 3? And now it becomes quite fun, right? So you just basically go up, copy and paste, and then change the limits. Well, because the PDF is the same, right? So the bounds are different. You just change from 2 to 3, and I get 0.1667, and that's the answer. Okay. What about the area under the entire x-axis? Okay. But remember, where's the sample space? The sample space is from 1 to infinity, right? So what do I do? Well, one way to trick the calculator into thinking about infinity is to enter something really large, right? So 2 to 9999 is really large because we see that 1 over 9999 square, that's almost like nothing already, right? So when we do that and let the calculator run for a while, all right, it will come back. Oh no, sorry, it's almost there because I started at 2. Huh? So what I'm trying to do is I'm trying to verify whether the area under the entire PDF curve is going to add up to nearly 1. Now, if I go to infinity, I should get 1, but I'm getting really close, right? I'm really getting really close. If you let the calculator run some more to 99999, 5 nines, you will get an improved value, nearly 1. And that's what we want to talk about. Because in continuous probability distribution, you also need to verify whether a function and the given domain, the given sample space, is it a distribution? Not all functions are distributions. How do you tell? These are the 2 points to tell. Came up in the exam before. That the function, the y-axis, the function on top is always on top of the x-axis. All right, the function is always on top, above the x-axis, and this means that the PDF of x for all the values of x, okay, in the sample space is greater or equal to 0, similar to discrete. Next thing is, if you add up all the area, this just means adding up all the area, all right, underneath the PDF function for all the x values inside the sample space, which is exactly our yellow area, isn't it? So when you do that, does it add up to 1? So similar to the discrete case again. Above the 0 or 0 or above, area add up to 1, or the heights add up to 1 for discrete case. Yeah. So these two criteria. Now then we say consider the function, same function, right? Check that it is a distribution. Then we say x squared is never negative, isn't it? 1 over x squared is never negative. So 0.1 is done already because this part is obvious. Second, we try to integrate from 1 to infinity, 1 over x squared. We check whether it is going to add up to 1. Of course, our calculator is already telling us very, very close to 1, so we are pretty confident. And when we do that, just now I said you check up the integration table that I gave you. 1 over x squared integrates to negative 1 over x. So that's it. We copy it down, and we are going to evaluate it from 1 to infinity. So we plug in negative 1 over x, where we have x, we plug in infinity, minus, again, negative 1 over x, where we have x, we plug in 1. 1 over infinity basically is to say it's going towards 0. So 0 plus 1, we have 1. And that's essentially showing that it is exactly a distribution. Okay? All right. So something similar above the sea level and add up to 1. Something different because we are checking PDF. We are not talking about the probability. Next is the cumulative distribution function, CDF. Now, we already learned that before. Thankfully, it is having exactly the same definition. In other words, it is the concept that counts. We want cumulative distribution rather than, oh, for continuous, then we have this, for discrete, we have that. No, it's a bit weird, right? Just because you count money by 1 cent, 1 cent, then your result is different from me counting money by a continuous flow of dots, something like a half cents or something. That shouldn't be. It should be the same. And here, the definition is exactly the same, but the way you do it has to be adapted to the function, right? The nature that it is continuous. So we use integration rather than summation as appeared earlier. So what do we do here? Consider the function 1 over 6, similar to what we have just now, but now it's a constant line, a constant line. Remember, PDF is the height of the curve, and the height doesn't change. So it's a constant 1/6. And we say find C of x equals to 2, C of x equals to, in general, a W. C of x equals to 2 means integrate from 0 to 2, right, 1/6. And there's no u inside the function, just du. Well, that's what we do. For a unit 1, so integrate 0 to 2, 6 du is as good as saying 0 to 2, 6 times 1 here, all right, and this 1 has got, or rather, this 1 is because of we have u to the power of 0. So in that sense, it's not really important to write it out explicitly. And if you do that right, basically we then stick in anyway it's here already. So we stick in a u and we factor out the 1/6 and all this. Now if you are good with this, then basically you can handle all kinds of integration problems. But when we are talking about numerical result, you can of course, right, use your calculator again, and we are supposed to do 0 to 2. So we can do 2 here. 0 to 2, 1 divided by 6, and that's it. Oh, yes. Okay. And dx, yeah? It will look something like this on the calculator. And is it 1/3? Yeah, it's 1/3. Okay, so as simple as that. So we verify that whether you do it by hand, the manual integral way, or you do it numerically, let the calculator take over, both are okay. But of course, if we ask you for a formula, then you can only use calculator to test whether your formula is correct. You have to derive the formula first. So this will be for those who are really, really into getting the last mark out of the exam, then you will be getting this right, okay? But it's just integration, looking up the integration table. Then we have another example, slightly more complicated, but we have seen it, 1 over x squared, same thing. Go through the motion, go by definition. The reason why I have 2 examples is to show you easy ones, we do like that. Difficult ones, we also do like that. There's no difference. It's the same treatment because it's the same definition. You're asking for CDF, right? So this is how I give it to you. I integrate until x, the point that you want, right? The point that you want. And then I give you this formula, 1 minus 1 over x. Therefore, no matter what x you give me, like 2. Just now we integrated 1 to 2, we get half, right? If I plug it in here, 1 minus 1 over half, 1 minus 1 over 2, that's half. I immediately get a result. I don't have to integrate all the time. So CDF function has that purpose, to always give us the value immediately, okay? Then similarly, instead of summation, we use integration, and luckily it's taking up the same form. You stick in an x, instead of integrating the PDF throughout, we use x times PDF and then integrate throughout, similar to the discrete case. Similarly, for variance, instead of integrating PDF directly, we integrate x minus the mean of x and then square it. Same idea as before. Although now it's harder to draw the square of each point and all that. It's harder to draw. That's why in the discrete case, we try to understand the concept. Come to here, it's hard to draw it, to see it, but the concept is the same because the formula is the same. Yeah? And also, after some expansion, we can then treat this as one unit and do our integration, find out the value. You can use your calculator, right? Then we can do the square of the mean, all right? One example here. Find the expected value and variance of 1 over 6. Now, don't jump the gun, huh? Oh, 1 over 6, some of you write, expected value therefore is 1 over 6. That's not true. We are finding the average, right? Average of x ranging from 0 to 6, all values being equally probable. That is not going to give you 1/6. it should be somewhere in between. So let's go through the proper procedure. We stick in an X to our PDF, right? Okay, then we integrate from the smallest value to the largest value, the whole range. And we can then do the pattern recognition to plug the already integrated results from the table, put it in here, evaluate, we get 3. And of course, if you stick in your calculator now, you should see that you should get 3 too. But let's do this, right? We want to integrate x squared times 1 over 6, all right? So we want to do 0 to 6 x squared, and we do that by saying that we want to say x, this is the x, and we want to square it, all right? Then we times this constant, which is, okay, is that right? X squared times 1 over 6, and we want to say dx, and that's correct. So the first red box will give us 12. I hope you can verify that. 12 minus 9, right, that will give us 3. So the variance is 3, yes? Okay, so you can check that numerically using your calculator. So all this is trying to assure you that you might be weak in the manipulation of the algebra, the integration, but hey, the concept has to be there, right? So if you're lucky, the exam question asks you for calculate the numerical values, then you can be assisted, and you can, you should, you must use the calculator to verify, right? But if it is a little bit more advanced, asking you for a formula for cumulative distribution function, then you need to do a little bit of manipulation. And I can assure you here that the most difficult CDF that I gave will be something that you can quickly find from the given table that I uploaded. It's not going to force you to do integration by parts or, you know, some advanced techniques and all that stuff. Clear? It's the concept that I need to know. All right. Now, as I said, I have partitioned the list of continuous distributions that you will encounter in this course into 2 parts. The first part is what you must know at the least for your quiz. Okay? And they are the basic but very important ones: uniform distribution, exponential, and normal. Right? So the formulas are given here. Exponential, you cannot be assisted by your calculator because your calculator does not have a distribution function for exponential. So you have to rely on these here. So let me also write in the CDF function that you can append to your slide here. CDF of little x is going to be equal to 1 minus e to the power of minus lambda x. Okay? So this will be useful because it gives us immediately the area to the left of x. All right, so this is useful. Now, for uniform distribution, application areas, intervals where they are all equally likely to occur. This uniform distribution in the continuous case has the most use where you are doing mathematical modeling. Very complex, yeah, that's what I say. Complex situation, and we want to build from scratch. So in the exam or quiz, we will probably come up with some excuses to say that we are approximating this complex situation using uniform. So then you will be using this set of formulas, right? So all events are equally likely to occur. Exponential distribution is very intimately related to Poisson distribution because, and this is something that we will also quiz you on, that when you are given a Poisson distribution, at the same time, an exponential distribution exists simultaneously, and here's how. Using my customers arriving to my cafe example, if I don't count by 10-minute interval, but I measure this guy, right, from time equals to 0, when did he arrive at the door, at the front door of my cafe? When did it occur? Because come to my front door, then I realize the customer has arrived, right? So let's say this is 6.33, and the space between the first customer and the second customer, the time interval apart, is an additional 2.49. I'm just giving random number. Just follow my story first, all right? So the time interval between second and third customer, another 7.31. This can be 8.52. Okay, you get the idea. I measure the time interval between consecutive events. Okay, let's say this is 5.31. And you get the idea, right? The numbers are not important. I just give them approximate numbers. If I measure the time interval between the consecutive events, they are consecutive, one immediately another. This is called the inter-occurrence time or the inter-arrival time of events. Events meaning my customers here, okay? It can be any other events like the arrival of a photon from Andromeda galaxy. But the time interval between events, if I measure them and I call that those sequence of numbers because they are another sequence of numbers of the same physical event, right? I'm looking at the same CCTV footage, isn't it? And I call those numbers Y. And if I put those numbers Y into a histogram and I say, how many times do I see occurrences of Y between 0 to 3 minutes? 1 time, 2 times, 3 times. You know, I do some counting like that. How many times do I see intervals that occur between 3 minutes to 6 minutes? And 1 time, 2 times, 3 times, and I do that. Okay, so again, I'm doing the same to convert a time series into a distribution. And you'll find that it will really look something like that. Okay. And what is this? This is, if you do it with sufficient fidelity, it should look, Y should follow exponential distribution based on the same lambda. Now notice these two, right? They are the same lambda because they are based on the same event having only one average rate of arrival. However, either I measure count of customer per unit time, per 10-minute interval, or I go by the measurement of the inter-arrival time. They both exhibit the same rate of arrival lambda, right? So if I go by the count, then I get Poisson. If I go by the inter-arrival time, I get exponential distribution. That's why they are so intimately related to each other. Yeah. So in perhaps one of your tutorial questions, we'll give you one practice on this. You get information, you get facts, you get data about Poisson, but the question requires you to think about exponential before you can solve the problem, right? Something like this. So this is implied knowledge. You should know this, and it's very, very powerful in that sense. Now, you can't calculate your CDF using your calculator, so here's the CDF. You also don't have the CDF for your uniform, but that's easy because you know the height, and the CDF up to a point X is what? It's the width times the height, yeah? So just X minus A times 1 over B minus A. So this is your CDF. As simple as that. You can just derive it on the fly. But what about the CDF for normal distribution? If I have a point here, X. Okay, let me draw it out here. If I have a point here, I have normal distribution. All right, and the X is based on 100 and a spread of 10. Then what is the area up to and including the point 90? On the left side, this will be the CDF of 90. All right. When you have this kind of problem, and it's very common to have this kind of quiz questions or tutorial questions, this is where your blue button comes in. Okay. So you see this distribution on top here. Okay. This is where you activate the second bars, and you see a list of distribution functions. Starting from the normal PDF. The PDF is what you don't need. We don't have questions asking you how tall is the normal bell curve. But you do need the CDF. Later on, you need inverse normal to give, if I give you the CDF, what is the value that gives rise to your CDF? Sorry. Yeah, that's right. Yeah. So let's do this normal CDF. You go from minus infinity. This is calculator's way of saying negative 1 to the power, 1 times 10 to the power of 99. That's very, very negative. Until the point 90, the mean is 100, the spread is 10. Okay, so when you do that, the area is 0.1587. Please do everything to 4 dp. And that will be your answer. Okay, does it make sense? Yeah, it seems right. Because it hasn't crossed the halfway mark, it should be less than 0.5, and that seems okay. Yeah. So a lot of the distribution functions can be found here. Normal CDF. Later on, the student T CDF, the chi-square CDF, and the F-CDF. They are all here. Okay, and something that brings me to the next slide. That is for awareness only. Don't have to kill yourself to try to memorize everything here, but it's to introduce to you that in this semester, we also have student T. You should know the T-CDF very soon, lecture 3 or 4. You will know, you will have to use chi-square, CDF, and the inverse. So what is the inverse? If I say, what is the value that gives rise to 0.1587? That is called an inverse problem. So we want to know the inverse norm of 0.1587 interpreted on the graph having mean of 100 and a sigma of 10. If you do that, then your calculator comes in and says, I pick the inverse norm, function 3 here, inverse normal. Inverse norm means inverse CDF of the normal curve. When you do this, it asks you, what is the CDF area? You say, because the quiz question says, 0.1587, right? So 0.1587. This area is always to the left. It's always known to the calculator as the CDF area, which means it's always to the left. Okay? Now, which curve, which bell curve should I interpret it on? It has a mean of 100 and a standard deviation of 10. So when you do this, what do you expect? I should get back a 90, right? Okay, yeah, exactly. More because I did a round off, so it's not exactly 90. But if you copy all the decimal places, you should get a precise 90. Yeah, so this is the inverse problem. Now let's do a quick look at your list again. You have inverse norm, and you have T-CDF, which you must do. You also need inverse T. You need all the CDF and the inverse CDF, okay? But here, very soon you will find that your calculator has chi-square CDF and F-CDF, but nowhere do you have chi-square inverse, F inverse. This is where you need to download the 2 apps from the NTU Learn under the calculator related folder. So I'll give you those 2 apps. They have been approved by university for use in quiz and exam. So you have to use those apps. Otherwise, you can't get the inverse for these 2. Okay? So I think that's all for today. See you next week.